Hello, welcome to the lecture of engineering mechanics. In this lecture, we will be discussing moment of inertia. Okay, these are the outline I'll be covering in this video. The moment of inertia, concept, parallel axis theorem, perpendicular axis theorem for various geometrical figure. What will be the formula for moment of inertia? It is a very easy topic. So have patience, we will learn everything. Okay, in a short duration of time. So let's start. So before going for moment of inertia, I want to discuss something inertia. Okay, if you first got the idea about inertia, then we can calculate moment of inertia very easily, because in the previous lectures we have already discussed about the moment of force, that is nothing but torque. Okay, similar way, if we know what is inertia, then what we will do, we will take the moment of that inertia, we'll get the moment of inertia. Simple. Okay, so now what is inertia? See, inertia means it is the resistance. Okay, it is the resistance offered by any object to changes. Okay, to changes of it. So I'm saying inertia. What is inertia? It is the resistance offered by any object. It will be offered by the object itself. Okay, so the object will try to resist any changes. Whatever changes we will try by applying some external causes, but the object itself will try to resist its changes in the object body. Okay, so let's see some example. Suppose this is a block. Okay, what I'm saying, this one having a mass of m. Getting my point? Yes. Suppose I'm applying a force of P Newton. What I'm applying? A P Newton force. Why am I applying this P Newton force? I'm trying to displace this object. Okay, in this direction. Okay, because the block is placed on a horizontal surface. Getting my point? Over here. So I'm applying a force of P Newton. But the block is not moving. Why? Because of the inertia. Okay, because I want to change its state, but the state is not changing. Why? Because of the inertia of the object. Here inertia is nothing but the mass in case of translatory. Okay, again I'll give another example. See, if I'll take an circle. Okay, this is suppose a circle. What I'm saying, suppose I'm applying a force. This is the center. Okay, I'm applying a force in the tangential direction, suppose like this. It is having a magnitude of P. What I'm saying, I'm trying to rotate this object in this sense. Okay, but the object, if the object will rotate, then inertia is less. If the object, if the object will rotate easily, that means the inertia of the object is very less. If the object is resisting the rotation, that means we will say the object have more inertia to the rotation. Here the mass was the inertia for resisting the translatory motion, because how it will translate? The mass will apply an action on the ground will give a normal reaction to the object, then you will calculate the friction force, because here the friction force is more than the friction force in this direction will apply, that will be equal to the applied force, so that the body is not moving. That is the cause. But here similarly, if we are trying to rotate this object, circular object, it is not rotating. Why? Because the object has the tendency to resist it. So whenever we are applying a P Newton of force at some certain distance, so if I will calculate the moment due to that force which will act at the center, that is nothing but force into perpendicular distance d. Okay, that is the moment I'm applying, but the object is not rotating. Why? See, these are the examples of inertia. Inertia is saying simply whenever, another example I will give you like this. Suppose this is a beam, okay, this is a beam. What I'm saying, I will take a, so see, this is a cantilever beam. I'm taking a cantilever beam, okay, one end is fixed. So you know, we have discussed the cantilever beam will provide an horizontal and vertical reaction, and it will also resist the moment. It will also resist the moment by the support. These are the three reactions given. Okay. Now I'm applying a load over here. What I'm trying to bend this object like this. Okay. If the object will resist its bending, then we'll say the object has more inertia to the bending. That's different inertia. So the inertia with respect to bending. Okay. There are two types of moment of inertia. I'll discuss. Here is the rotation. See, I'm saying what? The moment of inertia is two types. The mass moment of inertia. The second one is area moment of inertia. So, the mass moment of inertia is responsible for resisting the rotation. Okay, this mass moment of inertia is responsible for resisting rotation. The area moment of inertia is responsible for resisting the bending. Okay, these are the two types of inertia. See, this application of this bending of beams will be in the strength of material chapter, which is not in the engineering mechanics. And the syllabus of moment of inertia, as per as diploma is concerned, the syllabus is only restricted to area moment of inertia. Okay, area moment of inertia. Similarly, the same concept is for mass moment of inertia. The mass moment of inertia is not mentioned in the syllabus, but still we will cover, because why? Whenever we will discuss dynamics, okay, whenever we will discuss dynamics, the uses of the dynamics will require the mass moment of inertia. Whenever you try to apply the dynamics concept on a rotational object, in that situation you will be required to give the idea about mass moment of inertia. And here I will give the area moment of inertia, how to calculate area moment of inertia of different. Okay, in the last video we have already discussed how to calculate centroid of any geometrical figure. Okay, so you got the concept idea about inertia. So inertia is nothing but resistance to any changes. Suppose the body is at rest, then the body will try to be at rest. Why? Because of the inertia. If the object is moving at an uniform velocity of v, suppose the body is moving, I'm talking about the second case. If the body is in rest, that is the first case, the body will try to be in the state of rest. That is nothing but the Newton's law, the law of inertia. Again, the law of inertia has a second statement. What it is saying? It is saying if an object is in uniform motion, that object will try to be in that uniform motion. It is applying some force of P Newton and the object is moving with a uniform velocity of v, which is constant. Then the statement of Newton's law is saying the object will continue its motion with the same velocity because of the inertia. That is called translational inertia. Okay, so in case of translational motion, the mass is responsible for resisting the motion. In case of rotation, the mass moment of inertia is responsible. Okay, IA, mass moment of inertia. Here is the IA, area moment of inertia, is responsible for bending. Okay, so what are the moment of inertia? See, we have discussed about the inertia. Now we will take the moment of that. That will be the moment of inertia. About a specific axis, we will take the moment. That will be implies to mass moment of inertia. So let's discuss the concept of mass moment of inertia. So what is mass moment of inertia? We'll discuss. Okay. So simultaneously, I will give you what is mass moment of inertia and what is area moment of inertia. The concept I will clarify in brief, but I will not derive all the formula for different cases. Okay, just I will give you the idea how the formula has derived. Okay, for different situation. So I'm writing the area moment of inertia. In the opposite, I'm writing here the mass moment of inertia. This one is not in the syllabus I'm mentioning over here. Okay, here is the syllabus, but this concept will be applicable in the dynamics. Okay, so we will get the idea of both. So I'm discussing the mass moment of inertia first, then I will go for the area moment of inertia, which is in our syllabus. Suppose see, I'm taking, there is a mass, this is a suppose a mass. Okay, so suppose this having a mass of dm kg. Okay, what will happen? And I'm taking a reference axis. I want to calculate the mass moment of inertia about this. Okay, because see, actually I'm trying to explain in this way. There is an object like this, any random shape object. Okay, in that object I'm taking a mass of dm. Okay, small mass. I'm taking a small portion of mass. I will calculate the moment of inertia due to the small mass, then I will try to get the mass moment of inertia of the total object. Okay, so in this situation I'm saying this mass is at a distance of, perpendicular distance of this mass is nothing but how much? This is suppose r. Okay, so at r distance from the axis, I'm saying the object having a mass. What I'm saying, the object is rotating, because mass moment of inertia is concerned with what? It is concerned with rotation. This object, I'm saying, suppose this object is rotating at an angular velocity of omega. At an angular velocity of omega radian per second. Okay, don't try to get into what is omega, what is theta. Okay, these things will discussed in the dynamics part. So I'm just saying the object is rotating in this sense. Okay, so just remember, whenever any circular motion will be there, the velocity vector will be tangential to the circular motion. Okay, circle of the path of the object. Suppose this object is rotating, so this mass will also rotate like this with the same radius over here. Okay, the object will rotate it like this. What I'm saying, the object will having an velocity in this sense, because omega in this sense, so the velocity vector we will calculate b. The velocity vector is nothing but, in circular motion we will study v vector is equal to how much? V vector is the position vector cross omega vector. Okay, this is the formula we will discuss in dynamics. So no need worry. Suppose this is the velocity in this direction. That means the object is rotating in this path. Okay, in the circular path. So I want to calculate the mass moment of inertia of this object, total random shape object. Okay, so before that I should calculate the mass moment of inertia of the small portion dm. So that is nothing but I into the moment of this, how much? If I'll take, it will be r into dm. You will say, is this the mass moment of inertia you are talking about? No, see, this is the mass at a certain distance. So in the last video we have discussed the mass, whole mass in the object will be concentrated at a single point called center of mass. How we are calculating the centroid formula? So like the perpendicular distance from that axis, wherever we are taking the origin, and the distance, we are multiplying the distance with the mass, so we are getting the centroid. So this is the centroid. Again we have to calculate with another radius. So second time, twice we have to take. How many times? Twice we have to take the moment of the mass. That will give rise to mass moment of inertia. So this is, I will write r square dm for the small mass. Okay, for the small mass. For the total mass, how will calculate? Suppose there are number of masses are there, so I will write in mathematics summation of all this r square dm. This is the, suppose there are a number of masses are there, okay, like this. There are different masses are there in the object, dm1, dm2, likewise. We will calculate for all these, then we will get the mass moment of inertia of the object. Okay, this is the formula. Again, whatever I'm saying now, there is another way to write this. I will take this mass, then I will integrate over the total area of the object. What I will get? Integration of the same r square dm. This is nothing but the mass moment of inertia of the small mass. Then I will integrate over the total area. I will get the total mass moment of inertia. The mathematics, whenever you want to get formula for any situation, you will take a small portion. Then for the small portion, you will calculate whatever amount of information you require. Then you will integrate. You will get the total information. Okay, that is the way to calculate any formula in engineering. Okay. This is the concept about mass moment of inertia. How an object, suppose there are different type of object. There is a circular object, okay, there is a rod which is rotating, like there are many shape. We will take small masses, then we will calculate about a certain axis how the mass moment of inertia will be calculated. Okay, so no need to worry about mass moment of inertia. This is not in our syllabus, but the concept we have discussed. Okay, for the examination, I'm just removing this part. I'm writing something for the MCQ examination. What is mass moment of inertia? Okay, the topic is mass moment of inertia. So how we calculate the mass moment of inertia? By taking moment twice. So it is the second moment of mass, because we have taken 2 times the moment. Okay, this is the second mass moment of inertia. It is also called rotational inertia. Okay, it is also called rotational, because it is the resistance offered by an object to the rotation. Okay, this is also called rotational inertia. Again, I will say why it is used. See, one more thing we have discussed here. We are depending, this mass moment of inertia is depending upon the distance of the mass wherever the mass is presenting. Suppose, see, in the last video of force, we have said force into perpendicular distance the moment. So as the distance is increasing, the moment value, that moment means the rotational effect. So from the axis, the reference axis, if the moment you want to calculate the moment due to force, moment of a mass, anything you want to calculate, as the distance will increase, the rotational effect due to that will also increase. So if you have masses outer side, suppose like here at this distance, so as the distance from the reference axis is increases, okay, the distance of the mass from the reference axis, as it is increasing, what will happen? The moment also increase. Okay, so I'll write over here, mass moment of inertia is depending upon what? It depends upon location of what? Location of the mass. As the mass will be distributed at a longer distance from the reference axis, the mass moment of inertia value will increase. Okay, so finally, what is mass moment of inertia? It is nothing but mass moment of inertia, it is used to measure any object's resistance, a object's resistance to change, in its what? The rotational changes. It's rotational direction, okay, or I will say the here it is okay, okay, just for rotational changes this is responsible mass moment of inertia, okay. You just remember it, you have to take second times, okay, second moment of the mass, two times you have to take the moment. Once we calculate for a small portion we can get the idea for the larger one, okay, by integrating or by taking summation. So I is nothing but I is directly depending upon r, okay. As the mass of the object is constant, you cannot change the I is depending upon the r. As the distance from the reference axis, this is the distance r of the mass, okay. As the distance will be increased, the mass moment of inertia will also increase, okay. That means the object will resist more changes, okay. Now I'm giving you situation, see some situation I'm giving. The mass of the object is m. I'm giving you the m is the mass of the object, okay. You have to distribute this mass by your choice, okay. I'm giving you the free randomly, you can distribute this same mass m for different figure, then you will see which one is having more mass of moment of inertia. Suppose see this is an object, okay. What it is a disk, okay. This side it is a totally a solid disk, there is no hollow portion in the disk, okay. Again I'm taking an, suppose this is the shape of the object like this, okay. This one is an object, both this is having a mass m, here is also having a mass m. Again I'm taking an sphere, this one is a sphere, okay. In 2D I'm showing it is a circle, it's actually a sphere. Again I'm taking another one like this, see this one is a ring, okay. This one is a ring, this one is a sphere, this is a cuboid, this is a disk. For the same mass, can you say what will be the mass moment of inertia of this one, number 1 figure, number 2 figure, number 3 figure, number 4 figure? In which of these, out of these 4, in which case the mass moment of inertia will be more? See, the mass moment of inertia is directly depending upon the radius. As the mass will be distributed at a very long distance from the axis, the mass moment of inertia will increase. Suppose see, here also there is a solid portion, so everywhere the mass is distributed over here. So see, this is a ring, that means the mass is not present in the hollow section, this portion there is no mass. So all the masses, the same mass, all the masses has been distributed about a certain longer distance with respect to all these 3 objects. So this ring, I of the ring will be maximum, okay, will be maximum. Why it is maximum? Because the mass is distributed at longer distance, from the axis of reference, whatever axis we are taking. That's why, so whenever you want to get more mass moment of inertia, you should distribute the mass at a larger distance. Likewise in the here, suppose this is the door of your home, suppose, okay. Suppose I'm saying this is a door, over here there is a hinge, and connected to this there is a window, okay. This is a door, suppose this is a door, okay. This one is a door, this is the wall of the home. So here is a hinge. What I'm saying, suppose I will apply the force here to close the door, number 1 position, then I will apply number 2, number 3, number 4. So for easy closure, can you say where out of the 4 location, where should I apply the force? Same force. The same force I will apply, F Newton. Okay. How the magnitude of the rotational effect will be increased? That means you have to apply the force at a longer distance. That is here is the longer distance. As the distance will be increased, the rotational moment the moment value will also increase, because the moment in the first chapter we have discussed, moment is nothing but the perpendicular distance into the force. So the force is constant. Okay, as you will increase the perpendicular distance, the moment will also increase. Getting my point? So for closing a door, you should always apply. That's why you will see in your door there is this type of clamping is provided on the door at the outer edge. Why? Because of the easy closure of the door. Getting my point? So likewise, here also, whenever the mass will be distributed at a longer distance from the rotational axis, the mass moment of inertia will increase. For the dynamics application of this mass moment of inertia, I am giving you some formula that you should remember for the dynamics only. Rotational, if the rotational question will come from dynamics, then only this formula will be used. So I am taking 4 things. One is the ring formula I will give you. The second one for sphere. Another one will be disc. The fourth one will be rod. Okay, these are the 4 I will give you the formula for. See, a ring like this. Suppose this is a ring. Okay, this is a ring, and the center over here, this is the center out of which what I'll say, the axis is passing, about which we are calculating the mass moment of inertia. So mass moment of inertia of the ring will be nothing but, this is the maximum. Okay, that is nothing but mr square simply. Okay, or I will write for the particle also. For a small particle, I will calculate. Here I am taking another figure, that is a sphere. Okay, suppose this is a sphere. Okay, this one is a sphere. So for the sphere, I will write I sphere is nothing but, you should remember, it's 2 by 5 mr square. How it is calculated? By integration. Okay, we will take a strip, then we will integrate over there. Okay, if you take about a disc like this is a solid disc. Okay, the disc is solid, all the faces are like this. I'll write over here like this. Okay, so this is a solid disc. So in this case, I of the disc is nothing but mr square by 2, the half of the ring. Okay, for the rod, this is a rod, and here is the center. I'm taking the mass moment of inertia of this rod like this, and having a length of L. Okay, every object having mass is m. M is the mass for all the situations. So I of the rod is nothing but ml square by 12. Okay, for a particle, see, suppose this is the axis, and here I am taking a mass of m, like over here, small particle. So the moment of this mass about this axis, okay, about this axis will be I of the particle is nothing but mr square. the same. Second, you have to take the twice the moment of the mass. The same, I of the ring is equal to I of the particle. Okay, that is the maximum. Here is the disk, for sphere, for disk. Then we talk about a rod. See, I'm taking the center in all the cases at the center. Okay, but if I will change the axis, reference axis, what will happen? See, if over here I will take the axis over here like this. Okay, this is the suppose axis called y. Okay, this one was gg. At the center of gravity this axis was passing. This was the gg, ig, g axis. I will take this axis at certain distance, that is y. Suppose this distance is nothing but how much? The distance is suppose h. Okay, in each case you can take the distance is h. So in this situation there is a theorem for calculating the mass moment of inertia about an parallel axis. So this is called parallel axis theorem. Parallel axis theorem is saying, suppose you have this axis gg, you know the mass moment of inertia of this mass, any random object, you have the mass moment of inertia formula for this axis. You want to calculate the mass moment of inertia about another axis like this. There is another axis which is y. So if you know ig value, you can calculate the mass moment of inertia of the same object about the y axis. How will calculate? You will take the mass moment of inertia about the center of gravity ig, whatever known, then you will write the mass m, okay, that object mass, into the distance between them, the perpendicular distance between them. Suppose this is h, you have to take the square, mh square. Okay, mh square. That is the parallel axis theorem. If you know the mass moment of inertia about a certain axis, you can calculate about the other. Okay, suppose see how what I am saying. Suppose this is a rod. Okay, rod having a length of how much? This rod having a length of L. I am calculating, I know the formula for this center G. So Ig I know for the rod is equal to ml square by 12. This formula I know. If I want to calculate about this one, okay, about this axis, if I want to calculate about this point, this axis, what I will calculate? I have to calculate this distance, how much? Suppose h distance. Suppose just don't calculate about random distance, I will take another. So this axis, suppose this axis is passing at the end of the object. Okay, okay, so we know the distance of this because it is half, this is L by 2. So about the center, this is about the center. If I want to calculate I about this rod end, I about the end, I will write the same formula Ig, that is ml square by 12. Then I will write the mass, then I will take the distance square, that is L by 2 rho square. So in this situation I will get ml square by 12 plus ml square by 4. So you take LCM of 12, you will get ml square plus 3 ml square. So you are getting 4 ml square by 12, that is nothing but ml square by 3. Getting my point? So the mass moment of inertia of the rod about any end, okay, about any end is ml square by 3. But about the center of gravity, this, because see the ml square, suppose this is a constant value ml square. Okay, in the denominator you are what you are doing, you are converting, or I will say you are doing 12 partition of the mass. Okay, the object you are doing 12 partition. So the value of this one is very less comparison to 3 parts. Okay, you are doing 3 parts of the same ml square. So in this situation this one is greater. Why it is greater? See, if the axis of reference over here IgG, what is happening? the mass are distributed nearer to the axis, but here the masses are also distributed about a larger distance. So as the distance of the mass distribution increases, what will happen? The I value will also increase. Getting my point? This was all about mass moment of inertia. Okay. Similarly, we will calculate area moment of inertia, which is in our syllabus. Now we will discuss the area moment of inertia. Okay. Here we will discuss area moment of inertia. The similar concept, whatever we are discussed for the mass moment of inertia, we will replace just mass, we will replace with area, you will get the same situation. The concept is same. Okay, you are taking the moment twice. Here also you will take the moment twice of the area. We will take the moment twice, we will take the moment twice of the area. In the mass moment of inertia, we are taking the moment twice for the mass. Here we will take area. Okay. This area moment of inertia is concerned about what? It is concerned about bending. The application will be in the strength of material. Okay. In the civil structure and mechanical structure. But here in the engineering mechanics, we will just see the bending, the area moment of inertia for different figures. So this one is very similar to this, the mass moment of inertia. Here you have to take second moment of area. In the mass moment of inertia, we are taking the second moment of the mass. Here we will take second moment of the area. The concept is same. So I'm just taking a random, I'm taking first two axes. Suppose this is the x-axis, this is the y-axis. Over here I'm taking a random object. This is the object. Okay, this area, sorry, this is not an object, this is a plane figure having area A. Okay, total area is A. In this I will take an area, small area dA. This is dA. Getting my point? Now what I will do, I will calculate the second time moment about the x-axis. This is one is y, this is x. Okay. So about from the y-axis, it is at a distance of x. Okay. From the x-axis, it is at a distance of how much? Y. So if I will calculate the area moment of inertia, it is not mass moment of inertia, it's area moment of inertia of the small area. I will calculate about the axis x. What will be? It will be written like this. You have to take twice the moment into the area, small area d. You can write in this way, or you can do integration of this. Once you calculate the area moment of inertia of the small area, then you will integrate over the total area, that is x square dA. The same formula. If you want to calculate about y axis, you will take summation of about y axis. See, about x axis you are taking how much? Sorry, there is a mistake. See, over here you are calculating the area of this area, the moment of this area about the x axis. So the perpendicular distance is nothing but y. So you have to take twice the moment, y square dA. About x axis, y square d. Similarly, about y axis, you will write sum of x square dA. The similar concept. Okay, you can write in the integration form, that is nothing but x square dA. In the above, this one is nothing but x square, this is y square dA. Getting my point? This is the formula, generalized formula. Here also you are depending upon the perpendicular distance. Okay, directly. As the distance will increase, the value will also increase. See, in the mass moment of inertia, what is the difference about this? This is a plane figure. This is a 2D figure. Okay. In the 2D figure, in the plane itself, I am drawing two axes. But in the other 3D, in the mass moment of inertia, see the mass moment of inertia. Where is this? What is the figure? Let me show. See, in this, the axis was perpendicular to the plane, okay, the plane figure. But here, these axes are lying, okay, these axes are lying on the same figure, okay. So this is the difference. So in this situation, if I will be having to calculate the area moment of inertia about an axis which will be perpendicular to this both x axis and y axis and passing through this point, that will be called polar moment of inertia. Okay, polar area moment of inertia, that is izz. Okay, about zz axis, izz, that is will be represented as j is nothing but I xx plus I yy. This is the formula, but if you want to derive with the same principle, you will calculate how. You have to take this is the distance you have to take. Again you will calculate this distance, you will take the moment about this axis twice. So this is distance. How much this distance? This distance, if I'll write that this one is r, so r is nothing but x square plus y square. Okay, r square is equal to x square plus y square. Again if you want to calculate iz, you can do the same way, integration over r square d, the same thing. You have to just need to take twice the moment. Okay, that's all. This is the concept behind area moment of inertia. Okay, the x-axis is lying on the plane, y-axis is lying on the plane, and the z-axis is perpendicular to the plane. That is called polar moment of inertia, area moment of inertia. If you don't want to calculate the formula wise, you know, you can, I will give you the formula for x-axis, y-axis, but just add these two, you will get the polar moment of inertia. Okay, ixx plus iyy will give you polar moment of inertia. And the parallel axis theorem and perpendicular axis theorem we will discuss. Okay, the similarly parallel axis theorem here also. Here polar moment of inertia is not just xx. If I will take another two axes which are perpendicular to each other like this, suppose this axis, this is an axis, and here is also an axis. Okay, I will take another one, sorry, this one is axis. Okay, and perpendicular to this there is another axis. Suppose this is AA, this is BB. Okay, the area is, total area is A is the area. In the AA axis and BB axis, if you know the area moment of inertia about AA and BB about any two perpendicular axis, not just XY, in the plane, these AA and BB axis are lying on the plane. Any two axis if you know, you can write the polar moment of inertia as IAA plus IBB will be equal to J. Getting my point? This is the polar moment of inertia formula. Okay, in the centroid we were taking only once, the moment was once. Here in area moment of inertia we are taking the moment twice, that is the difference. So here units, if you want to talk about unit, area moment of inertia will be area having an unit of meter square. Y is a distance, distance means meter, meter square, again meter square, so it's meter fourth. But in mass moment of inertia, this one having an kg meter square, this is the unit of the area moment of mass moment of inertia. Okay, the unit, if one mark question will be asked. So this is the concept behind area moment of inertia. Now we will just discuss parallel axis theorem and perpendicular axis theorem. It will be over. Parallel axis theorem, see the similar concept. I am taking a random area. Again I am taking axis, see. This is the axis. Okay. Again I will take another axis, see. Here is axis, here is axis. These axes are parallel to each other. In this situation, what will happen? This axis suppose called xx. This one is uu. This is suppose vb. You take any two axes. Okay, and this one is at a distance of h. Okay, and and I'm giving you the distance between the u axis and y v axis, suppose t. If you know ixx, okay, if you know ixx, you can calculate I about you can calculate the area moment of inertia about this axis also. Once you know the area moment of inertia about a particular axis, by using the parallel axis theorem, you will be you can easily calculate about the other parallel axis. So simple ixx, you know, you will write, if you know ixx, you can calculate iuu is equal to nothing but ixx plus the area square, that is h square. Okay, the area times h square, like in the mass moment of inertia, that was mh square, here is ah square. Okay, ivb will be similarly ixx plus this distance. How much this distance? This will be t minus h. So it will be area times t minus h whole square. So similar way you can calculate about any parallel axis. What is perpendicular axis theorem? See, the perpendicular axis theorem is simply say what we have already discussed, the perpendicular axis theorem. If you have any whatever we have discussed, the polar moment of inertia, na, this one is nothing but the perpendicular axis theorem. That is, if you know ixx and iyy and these two are perpendicular to each other, you can calculate about another axis iz which is perpendicular to the both axes xx and yy. That is nothing but ixx plus iyy. This is called perpendicular axis theorem. What I am saying? If I will, so perpendicular axis theorem simply izz is equal to ixx plus iyy, or you can write iaa plus ibb. It is simply saying, if you know the area moment of inertia about any two perpendicular axes, you can calculate the area moment of inertia about an axis which is perpendicular to both axes. Suppose x and y are perpendicular to each other, okay, these are perpendicular to each other, then you can calculate the z, the mass moment of inertia about z, like this. See, this is x axis, this is y axis, there is another axis z. In the xy plane you have a figure, suppose I will draw like this. Suppose the figure is like this. Here is a figure. Okay, if you calculate ix, iy, you can, by the perpendicular axis theorem, you can calculate about iz, or you have another two axes, suppose in this direction it's iaa, or I will have another, that is ibb. If you know iaa, ibb, then you can calculate about the z both. See, these x axis, y axis, these are on the plane figure. The aa axis, the aa and bb are also in the plane figure, but z is perpendicular. Okay, this is the polar in the, it is a axis perpendicular, that's called polar. Okay, so the polar moment of inertia, the polar moment of inertia will be used, having an extreme use in the twisting of shaft in the strength of material. Okay, so this izz is nothing but ixx plus iyy. Okay, we have discussed already. So if you know ixx, iyy, you can calculate about an axis perpendicular to the both axes. Okay, that is called perpendicular axis theorem, parallel axis theorem. Now I am giving you some formula similarly whatever I have given for mass moment of inertia. See, I will give some xx, ixx and iyy formula. That means the area moment of inertia about x axis and y axis. If you want to calculate about z axis, it's your choice, you can calculate. I have already discussed the concept how to calculate. Okay, so I'm giving you some shape. See, suppose this one is a shape, another one is a square like this, the other one is a sphere like this. So for the first one, suppose this is the P and the depth is D, width, depth, for if you want to calculate about this axis or this axis, whatever axis you say, this one or about the center. Okay, so these are the center of gravity. Okay, here is the xx, xx, yy, if I'll write I of the rectangle, it will be nothing but xx, yy you can calculate similarly. Okay, so you have to take the base first, that is B, about the axis, whatever axis you are calculating. Suppose it's a horizontal axis, you have to take the B that is parallel to the axis. So you will write once B, then B dq by 12. This is the formula for rectangle. Okay, for square similarly, the B is equal to D. Here nothing but this one is A, this one is also A. So you will write A into AQ by 12. So it is nothing but A fourth by 12, that is Ixx. About the center of the sphere, I will write about O, this is the O point. About x, y, whatever you calculate, the same formula you will get, that is nothing but pi d fourth by 64. These are the formula. Okay, you just need to remember these are the three formula and you will be able to calculate. See, I mean it is Ixx is equal to Iyy. Whatever you take axis, you will get the same about this axis or this axis. Okay. So for the sphere, this one is the sphere, this one is the, you don't need to remember this one also, only you have to remember rectangle. Once you know these two formula, you can calculate the area moment of inertia for any random figure. See, for the sphere, if you want to calculate Iz, that will be nothing but Ixx plus Iyy. Iz will be passed through the point O, which will be perpendicular both the axis, xx axis and yy axis. In this case, you can write 2 times Ixx. So it will be nothing but pi d fourth by 32. This formula J, okay. This one having a wide use in the twisting of shaft. By using perpendicular axis theorem, you can calculate the polar area moment of inertia. Okay, and by using parallel axis theorem, suppose I am taking another axis, this one is axis. Okay, and this axis called AA. If you know the area moment of inertia about xx axis, you can calculate about AA axis. Suppose this is the distance called h. So I will write see, IAA will be nothing but BDQ by 12, that is nothing but Ixx, plus you have to write the area is nothing but B into D, then distance, the square of the distance, that is h square. So this will be the formula for IAA about a rectangle by using parallel axis theorem. Here we are applying perpendicular axis theorem. Getting my point? So these are the formula you should remember: BDQ by 12 and pi d fourth by 64. Okay, if you know these two formula, by the help of these two formula I will give you some complex figure. So in total you have to remember this formula for rectangle, for sphere, and you know the formula of area moment of inertia, nothing but r square dA. That's all. Okay, you have to take the twice integration of this one, or you can write the similar way: summation of r square dA having an unit of meter fourth. Okay, this is the unit. If you know this much of four thing, this one, and this is the general formula, you can give answer to any question regarding mass moment of inertia, area moment of inertia. Okay, if you need one more, I will give. That will be a triangle like this. Suppose this one is a triangle having a base B, height AH. If you want to calculate IXX, it will be nothing but BHQ by 12, not BHQ by 12. Okay, sorry, BHQ by 36, not 12. 12 for the rectangle, so it's 32. IYY also. About this you have to take first HBQ by 32. These are the formula which will be enough for calculating the area moment of inertia for any complex figure. See, I am giving you an I shape. Suppose there is the question is like this. This is a I shape figure. Okay, if I will ask you to calculate about this axis, if I will ask you calculate area moment of inertia of this figure. So how you will calculate? See, first you need to divide this one like this. See, you will calculate area moment of inertia for individual rectangle. The first one will be like this. This one is the first one. The second one will be like this. The third one will be like this. Okay, so what I will do in the same figure, I will do this one, number 1, number 2, number 3. Then I will calculate about the gravity, center of gravity of this area. Okay, about the centroid, not center of gravity, it's a 2D plane. So about this one, so I will be giving you the B, D, all the dimension will be given. Okay, that will be suppose H, and here is B dash, whatever, here B, H. You will calculate about this one axis. Okay, you will calculate about this axis for the number 1 figure. For the number 2 you will calculate about this axis. Number 3 you will calculate about this axis. Okay, once you calculate for the different figures, then you will use parallel axis theorem. Suppose the 2 for the second figure you got I2 value. Okay, by using BDQ by 12 formula. For the second one, the first one, you got I1. Okay, you got I1 using the same formula BDQ by 12. For the third one, you got I3. So the question is asking you have to calculate about the x-axis. So you will write by using parallel axis theorem. What you will write? Ixx of the total I section. Okay, for the total figure, you will write what? For the second, it is nothing but I2. Okay, for the first one, about the x-axis of the first one, you will write, for the first one you will write I1, you know, then you will apply this distance, whatever distance is this, you have to calculate. Suppose this one is the depth D, you have to check this much is how much? this much is d by 2. Again you have height h, so this one is h by 2. So d by 2 plus h by 2. So d by 2 plus h by 2. This is the distance. You have to take the twice, then you have to write the area, that is nothing but b into d. So you got ixx of the same. Similarly, you will calculate about the x-axis of the third area. You will calculate about this, you know this one, you have to calculate this distance. Okay, then using parallel axis theorem, ixx, this one you can calculate. Finally, you will write ixx of the symmetric figure, I figure, will be the summation of, okay, this one and this one. Okay, you have to write sum of these three, you will get the total area moment of inertia. Any complex situation, I am just giving you I. Any random figure you will be given like this. Suppose I will write another one. See, if there is a rectangular box, okay, no issue, and over here there is a semicircle, and you have to calculate about this point. I am giving you, calculate area moment of inertia about this axis. What you will do? For the semicircle, you will calculate the area moment of inertia about this one. The centroid formula, you know, this one is how much? This one we have already discussed, 4r by 3 pi in the centroid chapter. You will calculate area moment of inertia of the rectangle about this axis, xx. Okay. Then you will calculate the area moment of inertia about the semicircle like this. How much will be semicircle? For the circle, for the sphere, you know how much? For the circle, it's pi d4 by 64 about the OO. So for the semicircle, it will be half pi d4 by 64 into 2. So this one you will be calculating about this axis. You got ixx of the rectangle, then by using parallel axis theorem, suppose this is zz axis, you can calculate about zz axis of the rectangle. How you will calculate? Ixx of the rectangle plus the distance. Suppose this is the distance, whatever dimension will be given, h, you will write h square into the area of the rectangle, whatever b, and the depth is, suppose the depth is d, so you will write bd. So similarly, you can calculate the whatever question will be asked by putting the dimension into the figure formula, you will be able to calculate area moment of inertia very easily. Okay, this is very easy concept. So we have already discussed whatever we have discussed. I will show you the slides. So see, for mass moment of inertia we have discussed, then we discussed the concept behind this. Okay, that is nothing but r square dm. The only thing you need to remember, for the ring mr square by, this one will be used in dynamics, not in the syllabus. Okay, so these are the formula you need to remember for the dynamics part. Parallel axis theorem, the similar concept, the mass into the distance rho square. In the area moment of inertia, it was area into distance square. Okay, this is the concept regarding area moment of inertia. Next video we see perpendicular axis theorem and parallel axis theorem. By using perpendicular axis theorem, we can calculate the polar area moment of inertia. These are the three formula you have to remember: pi d cube by 12, pi d fourth by 64, then bh by 30. The confusion must be removed. X axis you have to take once. Whatever axis, about whichever axis you are taking area moment of inertia, you have to take once, then the other dimension will be cube of the other dimension. Okay, here also about x axis you will be taking the the width once, b, that is parallel to x axis, then the other dimension will be taken cube. Okay, likewise you have to remember these three formula. With the three formula, you can calculate I section, any random section, whatever will be given in the question, you can calculate very easily. So this was all the concept regarding mass moment of inertia and area moment of inertia. Thank you for watching. In the next video, we'll try to cover the dynamics part as well.